My name is Michał Kustosz, and I'm a senior data scientist in deepsense.ai. And today I wanted to talk about the one very important, but maybe with less publicity, important AI field, namely forecasting. So in the past decade or so, we've seen a spectacular revolutions in the two deep learning related fields, namely computer vision and natural language processing. So I think you remember those moments when AlexNet exceeded all expectations in the ImageNet competition, when ResNet surpassed the human precision in classification of images, Mask, RCNN, YOLO, and all those models. We had a lot of breakthrough, and now the era of stable diffusion, generative AI. So there are lots of revolutions here in the past decade. Similarly, in natural language processing, I think the greatest breakthrough was the embeddings. So word2vec. This graph here that you can see, it was most shocking graph ever to me when I learned machine learning. It was really eye-opening. Word2vec, Glove, and other embeddings. And leveraging deep learning had a great impact on natural language processing field. So transformers that are fast and can run in parallel, and the ChatGPT and all the large language models. So as you can see, there are lots of buzz here, lots of breakthroughs, and constant revolution. And we're changing the paradigm each 2 years. But what about forecasting? I challenge you to say one breakthrough moment in the forecasting field. So maybe there are some, but they were with less publicity and not so well known. And that is the topic that I wanted to talk about in today's presentation. So why is that? Did we have a revolution in forecasting, or it didn't happen in as the title of this presentation would suggest? But that was only clickbait, so don't worry about this. So I will talk about do we have some recent advancement in deep learning in time series forecasting, and why we are not talking about any breakthroughs in this field. So the structure of this presentation would be the following. First, I will talk briefly about the forecasting, the fundamentals. Then I will say about classical methods, so statistical, machine learning methods, and then I will bring the deep learning methods, the newest one, and how they compare with each other, how to use them properly. And then we will talk about the revolution. Did it happen or not? So, forecasting. Prediction is very difficult, especially if it's about the future. A clever man said that. I think it could be a motto of this presentation. But what kind of forecasting we are talking about? We're not talking about guessing who will be the next United States president in 2024, although I'm quite certain it wouldn't be me. But it's not this kind of prediction. We're talking about the time series prediction. So we have a lot of types of time series, but each time series is composed of data points on some even time space, so just a point by point. And we have many different kinds of time series. And so classically, we are telling about the time series with trend, with seasonality, with cycles. As you can see here, you have lots of examples of such series. Some of them have like yearly seasonality. Some of them are very noisy, and some of them just looks like a random walk. And the time series on the left is for me very interesting because it's price of average bond in Polish, so a class of one asset class of in the financial markets. And as you can see, from 2006 we had a clear trend. So the price was going up, 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 up until 2021, when it dropped like from a cliff. And who could forecast this in the beginning of 2021, that we would have such a sharp decline in the price of bond market? By looking at the historical data, you really can't say this. Yes. So now we have a question: how we can really distinguish what is forecastable and what is not? So I encourage you to look on those four examples. So the first one is the stock price of the Apple company. Second one is a time series composed of the time when the sun rises in Warsaw. The third one is the time series of the value of random dice throw from 1 to 6 values. And the second one is demand for electricity in a random town. So what is the difference in all those situations? Why we can forecast one time series and we cannot do this in the other case? So in case of the throwing the dice, you clearly can see that the next throw is not dependent on the previous throw. So forecasting the next throw of the dice by looking at the previous one doesn't make really sense. In other cases, it's really different, but we can see that sometimes we are looking at some events, like the sun is rising at which hour, and sometimes we are talking about some quantities. So when we are talking about the quantities, we can say that, for example, a baseline model that just gives you a prediction of the last seen value is really quite a reasonable one. And sometimes it is the case, but sometimes it is not. So as you can see, you can have multiple causes for those time series from data points to arise. And really, when you think about this, what are these causes that make the time series forecastable? So if you want to have a good forecast, you would like to know the causes. But it's really hard when we're talking about the statistical phenomenon, such as demand for electricity, because there are many causes, and you really have to come up with some statistical cause. And sometimes you can have one, and sometimes you are just lacking it. You have to have a large amount of past data. If you have just one observation, you really cannot see any trend, any seasonality. And also you have to have a future to past data resemblance. So when we talk about the time series of the throws of the dice, we don't see this resemblance because this is just random. So we need to have this condition. And also we need to see if the forecast itself influences the quantity we are foreseeing. For example, if we make a forecast for the inflation rate in a country, when it's high, the real inflation, because of the forecast, may rise even further, because people will see the forecast and adjust their actions according to the forecast. So you have to be cautious about this. So having those conditions, we can see that forecasting is applicable in many fields. And for example, predictive maintenance, predicting load for servers, demand forecasting, weather forecasting. Some of those projects we did here in deepsense.ai, we did a lot of projects here in some of these domains. So this is really doable and it's really useful. Let us see what are the methods, how we can achieve those forecasts. So first I will talk about classical methods. The most classical methods are the statistical ones, used not by machine learning engineers, but just statisticians a long time ago. So they are mostly based on autoregressions and combination of that idea. So guessing the future value based on the past values. So we have moving average, ARIMA, exponential smoothing, linear regression. They are really basic methods, but they have proven to be really useful. And apart of that, they are computationally not. They are really cheap computationally, and they are very interpretable. Many of these models are interpretable, which is a great value in evaluating the forecast in real life. And apart of the statistical methods, there are also machine learning methods. They are less classical, but as you may call classical machine learning methods, I also included them here. So I know you are familiar with many machine learning methods. So like gradient boosting trees, random forests, support vector regression, Gaussian processes. You can take your favorite machine learning model and use it to predict the time series values. And how do you do this? Because the machine learning model it's not the same as a statistical model, because you have to have a fixed input and also fixed targets. So how you can achieve fixed input by using autoregressive information? You can take the columns of the series and shift it with the time. So each column may shift it on a different time, and then you can have like a simulation of classical methods. But those machine learning methods are more versatile, so you can add any columns you like here. So not only the time series columns, but also some exogenous variables and anything really you like. So the machine learning methods proved really decent in time series forecasting, and they are widely used because of the versatility I talked now. But also they are more computationally costly, and also the accuracy it's not always the best. And apart from organizing your features, you need to have you need to organize your training and validation. So the best way is just to train on up until some point in time, and to validate on the next k data points, just to see how your model is evaluating. So this is the standard method, and this allows to avoid the leak in the model training. Apart from training, you need to think about what are you going to predict. So there are mainly two methods of prediction using statistical or machine learning. So usually when using, for example, statistical methods, you are predicting only one step ahead. So your target is only the next day or the next hour of the time series. And usually you need to have a larger horizon of your forecasts. So what do you do then? When you have one step ahead model, you can use your predictions as your past data. So if you have a prediction step 1, you can use it as the last data available in your next prediction. So you do this iteratively. The other way is the multi-step prediction. So having having all the data up until the time t, you want to predict the time t plus 1. And this is your first model. The second model, having the data up until time t, wants to predict the t plus 2 prediction. So really, those predictions don't rely on each other. And in this way, you are not compounding the error that results from predicting the data, making predictions on the data that are itself predictions. Because in this way, you can end up with really high bias, and your predictions may, with the length of the prediction horizon, will increase exponentially. And usually the better way is to do multi-step prediction, but you have also the high variance here, and there is a lot of complexity, because if you have so much models to train, usually it is very expensive to do. So what are the other methods? Deep learning methods. We are talking about the deep learning revolution. So let me introduce what the deep learning brings new here. So there are, as you may expect, a lot of deep learning models that are used to forecasting. Feed-forward nets, deep AR, transformer-based. This is a wide family. WaveNet, NBits, NHITs. So I will explain a few in a brief moment, but they all are leveraging the deep learning paradigm, so training a lot of layers and perceptrons and so on. So the first method was deep AR, and that was a method based on LSTM and so recurrent neural networks and long short term memory cells. So this was the first method that allowed to train a lot of groups of time series together in one model, and then to generalize not only training by on one time series, but on many time series at once. And it really was quite an advancement. Also, it became popular because you can do this on AWS out of the box, and they didn't pay me to say this. So it was widely used for a moment. But as you know, LSTMs are quite expensive to train and not so easy to do. So we have a new method, NBits, and that was a state of the art for maybe 5 minutes. The NBits is neural basis explanation analysis for interpretable time series forecasting. And the interpretability here is not very complex, because you only may have the composition on trend and seasonality, so it's not very interpretable. And the main architecture relies on stacking neural network layers. So as you may expect, you have when you have your time series, you separate it on the forecast period and the look back period, and the look back is like 3 times longer, and each block of your stacks does basically the same. So it just has a lot of fully connected layers, and at the end it outputs a look back and a forecast part of the data. And when you stack it and you have a lot of stacks here, you can have very accurate predictions, but there is a lot of complexity here also. So The successor of n-bits is n-hits. It is a better n-bits, so nobody uses n-bits. Maybe not nobody, but it's not as widely used for now. And the motivation for n-hits was to have a longer horizon of forecasting and less complexity. Because of the reason I talked about, that we have a lot of complexity when doing multi-step prediction, we need to find another way to do this without stacking more layers. So n-hits does this. It does it by multi-rate data sampling. It basically decomposes the time series into the components with different how do you say this, frequency. And so you are just sampling the data so that your input data is not as dense as it was, and you're also sampling the layers of this network. And when you do this and you stack these layers, you have a lot less complexity here, and you're achieving better results than n-bits. And the authors of the paper also said that they are achieving state-of-the-art results on 6 benchmarks, but I'm quite skeptical about this, because what are the benchmarks for the time series data? There are a lot of benchmarks here, and they differ a lot. And usually when some paper claims to have state-of-the-art results, it has another benchmark for it. And that is because you can have different granularities in your benchmark data, different forecasting horizon, which is essential here. You can add or not add exogenous variables. You can have cross-correlated series, hierarchical series. You can have different evaluation metrics, and there is no agreement which one is the best here. So you have a lot of benchmarks here, and it's really hard to compare the solutions with each other. But having said all of this, I think that there is one fundamental problem in comparing the field of forecasting with, for example, computer vision. In computer vision, you have one image which is 256 by 256 pixels, and with 3 colors, it is about 195 kilobytes. But consider the time series data. You have 10 years of hourly aggregated data of temperature, so it is a lot of data, you would think. But really, it's when you just encode this data, it's less than this one image. And now imagine that you have ImageNet or CocoNet with millions of images that are with high resolution. There is lots of data here. And when you are trying to have a machine learning model on such a sparse data set with so little information inside, you have to be overfitting. And if you're not overfitting, you are predicting something which is nonsensical because of the noise that in real life is often very, very, very strong. So I think that is the fundamental problem with the forecasting, and that's why we don't see so many breakthroughs in this field. So there was a comparison study done between deep learning and classical methods. And by classical, I mean statistical machine learning methods. And the simple statistical ensemble was shown to be 25,000 faster and only slightly less accurate than an ensemble of deep learning models. So you can say that the deep learning is achieving state-of-the-art results in terms of accuracy. but we don't have much breakthrough here. Like we are not getting magnitudes better. We're just doing a little bit more, a little bit better, because of the fundamental obstacles I mentioned before. And to train the deep learning ensemble in this situation, you needed like 14 days and $11,000. And to train the statistical ensemble, you have to have only 6 minutes of computational power and half of a dollar. Yes. So there's really non-comparison here. Okay, but now you may think I crushed the deep learning methods, but not so fast. Sometimes the deep learning methods are really the only sensible way you can approach the problem. For example, when you have lots of time series data that are correlated with one each other, you don't know the correlation. They're really intertwined. There is a hierarchical relations. You have a lot of exogenous variables, and the series is really strange. So you can't really do decompose. You can't really decompose the series to stationary form. The deep learning methods has a lot of advantage here. So having those two methods, two sets of methods, if we had to compare those, I would say that the classical methods are easy with computation and interpretable, but they're best if you have, for example, one time series, and you have one model per time series. It relies mostly on autoregression and performs worse on many benchmarks. But the deep learning methods are computationally inefficient often and not much interpretable. There is some level of interpretability, but it's not very high. But it is better if you have a one model for a lot and lots of this time series and a lot of external, very strange data, because neural networks can devour everything you can give to them. And they perform better on benchmarks. So you may say you can win competitions with deep learning ensembles. And what about the real life? So in deepsense.ai, we do projects in real life. So in real life, there are many reasons why this more sophisticated solutions are not desirable. So the data is often very dirty. You have to, like 90% of your time is data cleaning. So you do a lot of cleaning and you're not sure that you did the right job here. So the interpretability matters a lot for lots of domains here. And when you're trying to maintain sophisticated solution, they are more prone to error. So sometimes it's better just to use linear regression, and it solves all those problems at once. So to conclude, we did not see a deep learning revolution in forecasting, mainly because of the fundamental problems with the time series data, overfitting and noise. But in many cases, the deep learning methods are better and only one that can be used with some degree of success. And while machine learning, deep learning solutions tend to have better accuracy, in real life, it's really simpler. The simpler solutions are the winners here. So thank you for this presentation, and I look forward to your questions.